Hello friends. So in continuation with the last lecture, now we are going to understand that how to improve the base transport factor in the PN junction. Okay. So to understand this, what we should have, we should understand that the uniform doping profile which we have in the PN junction, okay, or the in the base layer is actually has to be replaced by the distribution which is shown in this figure, right? So this is something like the typical doping profile for this silicon bipolar transistor. Okay, transistor in the sense that okay, it is having the 3 times p, okay, emitter base and the okay, emitter base and the collector, okay, with the some kind of the impurity gradients present within it, because earlier it would have been something like okay, a straight line would have been happening because it is something we call it as a uniform distribution, and then later we'll be having the like steps within it. But here what, instead of having the steps, it is kind of the gradient, you can see, or the curvature it has been shown over here, right? And as we can see here, that the with here the impurity gradient in the base clearly seen from this one, and heavily dipped region under the collector one. Okay, so the okay, this can be seen in this diagram. Okay, now actually in a transistor with such a base doping distribution is called as the drift transistor. Okay, why? Since its built-in electric field enhances the electron transport um, in the base by the drift action. Drift action is something like okay, drift is something like that, just moving little bit behind, okay, little bit behind, okay, and it can just move ahead by the some kind of the action, okay, and that action is done by the electric field. So the base density, okay, so here what we can have, the base density that is represented with the nb of x, okay, and the whole density in the base, okay, whole density in the base are related by uh, related to the Fermi energy level by the given equation, that this is something like we call it as a whole density in the base, okay, p of x, and this is equal to the or approximately equal to the base density, okay, base density, that is nb of x is equal to ni, this uh, intrinsic electron density into the exponential of the ei minus ef is a normal equation which we have seen many times. Okay, now since the Fermi energy level, okay, ef is a flat, okay, it is a flat in the neutral base, okay, it will be flat in the neutral base, and we can often the built-in electric field is given by something like the gradient of the intrinsic energy level, gradient of the intrinsic energy level divided by its charge, that is 1 by q times the gradient of the intrinsic energy level is equal to the uh, kt by just try to differentiate this equation by considering the ei ei is a function of the x, okay, ei is a function of the x, so what we can get it, the kt by q nb dnb by dx. So we just try to rearrange the terms in this equation and get the expression for it. So now the electron current here includes the both the factors, that is the drift current, okay, the drift component as well as the total current, okay, drift component as well as the total current, drift component coming from the this electric field, and the total current becomes the in of x is equal to aeq times mu n np into electric field plus dn dnp by dx. Okay, so now just try to substitute the value of the electric field in this equation, okay, so try to substitute this electric field from the above equation, and what that equation becomes, okay, that equation becomes the in of x aeq and dn np by nb dnb by dx plus dnp by dx. Okay, do remember these factors. Okay, so the steady state solution which the boundary condition at np of w. Np of w is something like we are trying to apply the our boundary condition at this place. Okay, at np of x is equal to w. Okay, and that becomes a 0 at that point. Okay, because we are talking at the boundary on the right hand side of the base. Okay, so that will result us into the np of x is equal to in of x a by q into dn into 1 by nb integration from 0 to w, because we are trying to cover the whole the base region, nb of x dx. Okay, and okay, so this is the equation what we can have here. Now the electron concentration at the x is equal to 0. So electron concentration at this point, okay, what we are talking about at x is equal to 0. Okay, is equal to or what we can say, electron concentration at x is equal to 0 is given by this equation. So we are just trying to substitute the value of the np of x is equal to 0 is equal to, we are just trying to understand this equation ine because this is at the emitter one. Okay, this is at the emitter because we are just at the boundary between the collector and the base. So at x is equal to 0, what we are trying to understand the electron conduction at this point, at that boundary. Okay, so ine upon a q dn nb of x is equal to 0 integration from 0 to w nb of x dx. This is approximately equal to np 0 of x is of 0 exponential of the some qba by kt. qba is nothing but the potential applied between the base and the emitter. Okay, so using the relationship earlier, that is nb of 0 into np of 0, np 0 of 0 is equal to ni square. So under the no biasing condition, so the electron conduction is, so the or electron current is given by this equation, that is ine is equal to ae q dn ni square upon this integration 0 to w nb of x dx and the exponential term. Here what we can see is the integral becomes, okay, so this integral what we can have here is the a e q n dn ni square upon nb dash into exponential term. So what is nb dash? So let's see, understand this integral, that is nothing but the nb dash is equal to integration from or is defined to be the integration from 0 to w nb of x dx, and is called as the total impurity per dose. Okay, it is called as the total impurity dose per area inside the neutral base, and is called as the Gamel number. Okay, it is called as the Gamel number, that is a nb dash. Okay, so now for the typically for silicon bipolar transistor, the Gamel number is around 10 raised to 12 to 10 raised to 13 per cc. Okay, so what it gives us, the Gamel number gives us the total impurity dose per area inside the base region. So now we can notice here that the for the injected electrons, okay, injected electrons, that is okay, injected electrons current, okay, injected electron current ine, which we have seen over here. Okay, uh, what matters is the total base dose or the Gamel number. So the actual doping distribution does not affect the ine, and the main function is to create the built-in electric field to increase the electron current inc. So what is its purpose? To have the actually the doping distribution does not affect the ine, but what we can have, its main function is to create the built-in electric field, so that the it can have the more drift of the electron present within the base region, so that the uh, collector current can be increased. Okay, uh, and this obviously uh, uh, improves the base transport factor, that is alpha t. So this also in addition with this, the whole distribution current injected from the base into the emitter. Okay, now when the electron is going from here to here, obviously hole will try to move from here to here, okay, base to the emitter. The whole diffusion current injected from the base into the emitter is the main component of the base current. Okay, so what is the main component of the base current? That is the whole injected from the base into the emitter is the main component of the base current. So the equations governing the whole distribution and the current are similar to the our general PN junction. So assuming here we are trying to assume that the WE, that is width of the emitter, is always less than its uh, d by length. Okay, so this current is given by IPE. Okay, so this current is given by this equation, getting it? So IPE, this is because of the holes at the emitter junction, is equal to the AEQDPE to PNOE upon W. Capital E stands for the at the emitter one. Okay, and then the what we can have, the QVB, this potential biasing. So now another component for the base current is via a recombination in the base emitter junction. So how much amount of the recombinations happening at this point? Okay, this is also the another component in the base emitter, another component for the base current, which is what we can say, which is also the responsible factor. Okay, so there are here the two recombination mechanisms in this region is happening. Okay, two recombination mechanisms are happening. One is because of the Shockley Reed Hall type. Okay, one is because of the Shockley Reed Hall type. Okay, this is the one of the mechanism, and which has means okay, so that already it is discussed somewhere else. And the another is the OJ recombination. Okay, sorry, OJ recombination, and which occurs when the holes are injected into the heavily doped N plus region, that is into the holes are injected into heavily doped emitter, and it is a direct recombination between the electron and hole. So what how much amount of these are injected into the heavily doped emitter? This mechanism is the direct mechanism, uh, or direct recombination between the electron and the hole. So and accompanied by the transfer of the energy to the another electron. So such a process involving two electrons. Okay, so in such a process, what happens that in OG electrons, two electrons contributes, and the one hole, okay, is taking part in such a recombination. Okay, so is the inverse process of the avalanche multiplication. Yeah, this is what the all about the how to improve the base transport factor in the